Okay, so for this lecture, you guys will need your cellular metabolism packets. And when we talk about metabolism, one of the initial things that I kind of need to talk about is that metabolism has been made out in the media to be something that it's not really. And just to kind of reframe our minds as to what metabolism is actually talking about when we take a look at it. So, metabolism right now, people immediately go to fast metabolism, I'm going to lose weight, slow metabolism, I'm going to gain weight. And there's a lot more to it than that. When we talk about metabolism, what we're actually looking at is we are looking at the amount of work your cells do in a given period of time. So if you were to look at a 24-hour window and take every cell in your body and measure how much work it did and then add all of that together, that is going to account for what your metabolism actually is. Now, through the process of metabolism, you're really doing one of two functions. You are either going to take something small and build it together to make it bigger, or you're going to take something big and you're going to break it down into smaller components. So if you think about a puzzle, you open up a box and all the individual pieces are sitting there, and then you go through the process of finding the or linking those individual pieces to construct the entire puzzle. That is one process of metabolism. You get the puzzle done, you need it to go back into storage. So you take all the pieces apart, throw them back in the box. That is a second part of metabolism. So it's all the work that your cells do in either building things up or tearing things down. And the reason that we need to either tear things up or build things up or tear things down is because we supply fuel to our body through food in a roundabout way. How food initially goes into our system is of absolutely no benefit to it whatsoever. If you think about the things that are in your body, you have muscles, you have bones, you have all these different types of cells, tissue, DNA, all these different materials. And then if you align that with what you had yesterday for food, think about what you had for breakfast and lunch and dinner and snacks in between. There is nothing in your body that is made out of any of that. Even if you ate the healthiest diet on the planet yesterday, there is nothing in your body that is made out of any of those directly. Even if you had a horribly poor diet yesterday, again, there is nothing in your body that is made out of those foods directly. So, by the foods that you put into your body, what you're essentially doing is you are giving your system a a chance to have access to all of these different types of materials, all these different atoms and elements and minerals and nutrients. So when you put pizza into your body, you have tomato sauce, you have cheese, you have the dough, and in that cheese, you're going to have some calcium. Well, the cheese, there's nothing in your body made out of cheese. So what does your body have to do? It has to take those large food molecules and break it down and get those individual components separated out so that that calcium is just by itself. Some of the other things that you have in pizza are going to be made out of water. You'll have water in the tomato sauce. Well, you're going to separate that out so that you get just the water by itself. If there's anything that was made out of carbon, you're going to break it down so that just the carbon is by itself. So that it started out as pizza, but by breaking it down into the individual components, you now have available to you all of the minerals and the nutrients and the vitamins. And then your body can go through and say, okay, we need to build DNA. And to build DNA, we're going to need this ingredient, and this ingredient. And it pulls those from what you've provided your body through food, and then you will link those together and recombine them into what your body actually needs. So you introduce them in kind of a lump sum through the food you eat. Your body breaks it down, individualizes all of the things that you've provided your system, and then you go through and pick and choose and select how to recombine those and build it back up into what you actually need so that you have good strong bones and you have muscles and you have DNA and all of those other materials. So the process of metabolism is much different than how it's typically portrayed in commercials and things like that. So when you look at your packet, I kind of introduced without actually using the terms. I talked about tearing down and building up. And that's those first two terms that you guys have on page 1, anabolism and catabolism. So in the process of anabolism, you are going to take small individuals and you are going to link them together and create a larger molecule. In catabolism, you're going to start with that large molecule, you're going to break it down into its individual parts. So anabolism, we are going to build up, catabolism, we are tearing down. Now, in order to do that, the slides that you have on the bottom of page 1 and the top of page 2 are going to give you the visuals behind that. Now, my fear in putting these slides in, they're very important for you guys to see, but initially people get so fixated on all of the letters and the subscript numbers and thinking that they have to know what all of those are. You don't. When you look at those two images that are in the packet, all I need you to do is focus on the fact that there's two molecules on the left and they're linked together so that on the other side, there's one bigger molecule. So in anabolism, on the left-hand side, we have two molecules. They're by themselves. We take them through a process of dehydration synthesis, and then we link them together, and now we have a larger molecule. That's really what you need to put your focus to. Now, with anabolism, goes back a little bit to our chemistry chapter. We talked about water, and water seems like it's so boring. But this entire process is very dependent on either forming water or adding water. Now we have those two individual components, and even though you don't need to know what each and every one of those letters means and indicates, that's on the edges of the hexagons, if you look at them just very briefly, you'll notice that some of them are H's and some of them are O's. And you guys know that water is H2O. And also through our chemistry conversation, when your water molecule breaks apart, when it dissociates, you have one hydrogen that goes off by itself and it has a positive charge to it. And then you have one of the hydrogens and the oxygen that go off together and they carry a negative charge. Why is that important here? Because when you look at those two molecules on the left, and if you think about the fact that, okay, let's pull out one of those hydrogens. Well, when we take that hydrogen, it's going to take a positive with it. And it leaves behind a molecule that's now going to have a charge. The other side, if we take an OH off the other molecule, it's going to take a negative with it. And now we've left that molecule with a charge. So laws of attraction say opposites are going to attract. If we pull off an H plus off of one of those molecules, and an OH negative off the other one, we've left a positive and a negative charged molecule behind. Opposites attract. Those two individual molecules are now going to link together through those charges, and we have built a larger molecule. Now, because we stripped a hydrogen, or two hydrogens essentially, and an oxygen, that makes a water molecule. We pulled water out to make this happen, and so when we remove water, that is known as dehydration synthesis. So when you look at anabolism, we're going to remove a water molecule. In doing that, we create charges on the molecules. They attract to each other, link to one another, and they combine in that form. And this just shows two, but in the body, you could have a molecule that's hundreds of elements linked together, and it could be a very, very long chain. This is just a simple one that it was showing you. If you move over to page 2, it shows you the same process in reverse. So now we have this large molecule to begin with. We need it to be smaller. And so now we're going to introduce that water molecule. Water molecule dissociates, and we have this hydrogen with a positive charge and an OH negative with a negative charge. And it's going to work into that molecule and form bonds with those individual molecules that are there. So you have your one big molecule, this water comes in and it starts reforming bonds with the molecules. And in doing that, it breaks them apart. Because we take water and we add it to this system, it is known as hydrolysis. So when we are building something, then we are going to use dehydration synthesis. When we are tearing it down, it's because we added water, and we are going to refer to that as hydrolysis. the other big thing that happens within the human body that deals with metabolism is going to be the use of enzymes. Enzymes are these amazing little structures. They're made of protein and they are reusable. They can be used over and over and over again, which is hugely important to our survival because of the number of enzymes that we use on a daily basis. If we had to rebuild them, if they were one-time use and we constantly were having to remake enzymes, we would never be able to survive, at least not the size that we are now. So enzymes, protein-based, they're very strong structures and they are able to be used time and time again. Now, why are they so important? Because enzymes are going to speed up things that normally would take so long to happen on their own. We would never be able to survive. We would be waiting so long that things would not happen in a timely enough fashion that we would be able to exist. So enzymes take the amount of energy that it takes to get a chemical reaction to happen, and it lowers that amount of energy needed, and it just makes the reaction happen faster. Now, enzymes are really neat, and they do a lot of great things, but we don't want them working all the time. There's sometimes you don't want a chemical reaction to happen in the body. And so in order to make sure that enzymes are only used when they're needed, they have a counterpart, which is known as a substrate. And until you take the enzyme and the substrate and you link them together, the enzyme can't do its job. It can't speed up the chemical reaction. It's kind of like if you think about the locks on your door. You have the lock on your door, but until you take that key and fit it into the lock, that door is not going to open for you. It's not going to give you passage. And likewise with the enzyme, until you take its key, the substrate, and lock it into the enzyme, you're not going to be able to carry out that chemical reaction. So enzymes, protein-based structures, they are designed to speed up reactions that would otherwise take an amazingly long time to happen in the human body. And they allow us to work at a much more efficient rate than we could by ourselves. Now, you can regulate your rate of reactions based on one of two things. If you want a chemical reaction to happen and you need it to happen for a long period of time, you would increase the number of enzymes that you have in the body. More enzymes, the more that chemical reaction is going to happen. You also can regulate it by the number of substrates. You could have 1,000 enzymes floating around in the system, but if there's only one substrate, then that one substrate can only match up with one enzyme. That chemical reaction is going to happen at a very, very small rate. But if I have 1,000 enzymes and I release 1,000 substrates, now all of those enzymes can be put to work and that chemical reaction is going to be much greater. So your body can regulate the intensity of a chemical reaction, how fast it happens, based on the number of enzymes that are available and the number of substrates that are available. If you look at page 3, talks a little bit more about controlling your metabolic reactions. And then it talks about the process of cellular respiration. And I'm not going to spend a huge amount of time on this. I introduce it here, but we come back to it in the respiratory chapter. But I do want to spend just a couple minutes on it. Cellular respiration. When we say respiration, we think breathing, which is very true. When we add the term cellular respiration, now we are talking about using a very important molecule at the cellular level. So when you breathe in and out, what is the molecule that we typically associate with that? Oxygen. We're trying to get oxygen into those lungs. But it doesn't stop there. Once you get that oxygen into your lungs, it hasn't done anything yet. It is of absolutely no benefit to you. You have to get that oxygen from your lungs into your bloodstream, from your bloodstream into your cells, and then once it's in your cells, it has to get all the way into a tiny little organelle known as the mitochondria. Once it's in the mitochondria, now the oxygen can really be beneficial to the human body. So when we talk about cellular respiration, it's about making sure that that oxygen is actually delivered to a place in the body where it can be put to work. So cellular respiration is a 3-step process. It starts with glycolysis, and then it goes to the Krebs cycle, and then it goes to the electron transport chain. Now, the entire goal of cellular respiration is to build your fuel source known as ATP. ATP is the equivalent of gas to your car. If you want your car to go, you put gas in it. If you want your body to work, you have to give it ATP. So everything that happens in cellular respiration is designed at building this molecule known as ATP. Now, ATP stands for adenosine triphosphate. Adenosine is a base molecule that has 3 phosphates attached to it. Now, the one thing with these phosphates is they're high energy molecules. They have a ton of bonds that make them up. And anywhere that you have bonds, you have energy. So if you break a bond, you release that energy into the surrounding system. In this case, your cells. So what happens is, through this process of cellular respiration, we're building these ATP molecules. And then when your body needs energy, it breaks off one of those 3 phosphates, breaking the bond, releases energy. Now your cells have the energy they need to do work. So looking at the process of cellular respiration, the first step, known as glycolysis, is going to produce 2 ATP molecules. Now, glycolysis, glyco indicates sugar. Anytime that you see glyco attached to something, it's telling you that you have a carbohydrate or a sugar attached. Lysis means to break or to destroy. So the word glycolysis literally means to break or to destroy sugar. That is going to, when you break that sugar molecule, breaking bonds, we're getting that kind of jumpstart energy to drive the process of glycolysis so we can really start building some ATP. So in this first stage, we break the sugar and go through the process of glycolysis. We get 2 ATP molecules at the end. Then it moves into the next phase, which is known as the Krebs cycle. Some of you might have learned it as the citric acid cycle. You can use those 2 terms in place of each other. That's fine. Excuse me. It's called a cycle because it happens twice. So it goes through the cycle and then it repeats the process again, and it has that circular shape. And so you have 1 ATP that is produced in each cycle. And so at the end of Krebs, you have 2 ATP molecules. So 2 at glycolysis, 2 more in Krebs, and then we get to the electron transport chain. And here's where the electron transport chain, or ETC, is so vitally important, because at this point, it's where we're finally going to get to that oxygen molecule. Now, when we talked about oxygen earlier with the water molecule, I described it as a bully. It took the electrons away from the hydrogens, pulled it closer to itself, and essentially oxygen does the same thing in the mitochondria as well. The oxygen is going to draw these electrons to itself. And as those electrons are getting drawn to the oxygen, it creates a current within the cell that is going to provide all of this energy so that the cell can produce tons of ATP. So with the electron transport chain, you had 2 ATP from glycolysis, 2 from Krebs. We get to ETC, produces 32 ATP molecules by itself. It blows the other 2 out of the water. It's not even close. And it all has to do with the presence of that oxygen molecule. So we inhaled it, got it down to our lungs, traveled through our bloodstream, got delivered to our cells, ultimately ends up in the mitochondria, where it starts pulling all of these electrons to itself. And through that process, we can create an amazing amount of ATP molecules, which is our fuel source. So when we look at cellular respiration, really trying to build that ATP, our fuel source. And again, the pictures can be intimidating. You've got all these arrows and these molecules and abbreviations that you really don't hear that often. And you don't want to get caught up in that, not for our purposes. If you just understand that the whole goal is getting that oxygen molecule positioned strategically so that it can create a current with those electrons and really allow the body to be very efficient at producing ATP molecules and that final stage of cellular respiration, that's the key component to it. So that takes us to page 6, the last part of the packet. I know it talks about DNA, and this we're going to pick up in cells. So when we get to our cell chapter, I will just move that information over there and we will talk about the structure of our DNA.